Okay, so you're someone who really wants to get to the bottom of how the universe ticks, right? Always chasing those aha moments, those flashes of insight that just click.
I know that feeling.
Well, strap in because today we're diving deep into one of the biggest mysteries out there, unifying quantum mechanics and Einstein's theory of relativity.
Oh, this is going to be good.
Seriously, it's a journey to the very core of reality built just for you based on your curiosity.
I love it.
You sent us some fantastic starting points, too.
Yeah. What did you have in mind?
Especially that A Brief History of Eternity book really hit on those big questions we're tackling. How does the quantum world connect to what we see every day? That deep link between mass, energy, and gravity, the whole mystery of time, even, get this, the possibility of time travel.
Whoa.
No kidding. So our mission today,
Hit me with it.
we're extracting those golden nuggets of insight from these seriously complex topics. Clear, engaging, just for you.
Love the sound of that. What always gets me is the sheer boldness of trying to do this. I mean, we've got these two giants of physics, quantum mechanics and relativity, both unbelievably successful in their own realms. Quantum for the super tiny, relativity for the vast cosmos. But when you put them together, their descriptions of reality clash. Hard.
You're telling me it's like on one hand, you've got quantum mechanics with all its fuzziness and probabilities at the smallest level. Things can be in multiple states at once. Then on the other, you've got relativity, giving us this smooth, deterministic picture of space and time on the grand scale. How do we even begin to bridge that gap?
That's the million-dollar question. Let's start by really understanding those differences, right? Comparing the quantum world to the macro world we experience, and even those simpler binary systems that run our tech. What are those core fundamental differences we need to get our heads around?
Right, because down at the quantum level, it's like the rule book goes out the window. You've got superposition, where a particle can be in multiple states simultaneously until we actually measure it. Like, it doesn't make up its mind until we peak.
It's wild, right?
Totally. Then there's entanglement, where two particles are linked no matter how far apart they are. Mess with one, the other reacts instantly. It's spooky action at a distance.
Einstein wasn't a fan of that one.
Nope, not at all. And of course, the uncertainty principle. You can't perfectly know both a particle's position and its momentum at the same time. It's fundamentally blurry down there.
Reality's playing hide and seek.
Exactly. But zoom out to the macro world, the world we live in, governed by classical mechanics. Everything feels solid, predictable.
Cause and effect.
Exactly. Know the starting conditions, you can predict what happens next, at least in theory.
In theory, absolutely.
And it's all local, right? Things are only affected by their immediate surroundings. And then you have those binary systems, the ones and zeros driving our computers. Ultimate clarity, on or off, no in between. Such a contrast to the quantum fuzziness.
Night and day.
Totally. So we have this huge gap in how we describe the universe depending on where we're looking. Now let's bring Einstein's relativity to the table. How do special and general relativity change our understanding, especially with this gap in mind? What did Einstein throw into the mix?
Well, relativity shook the foundations of our understanding of space and time. Special relativity, which came first, revealed that space and time aren't these separate, fixed things.
They're not.
Nope. They're intertwined, woven together into this single fabric, space-time.
Space-time.
And at the heart of it all is this idea that the speed of light is constant for everyone, no matter how fast you're moving. This messes with how we measure distances and time.
So the stage where the universe plays out isn't static. That's a game changer. And then general relativity comes along. How does it build on this, especially when it comes to gravity?
General relativity revolutionized our understanding of gravity. Says gravity isn't a force pulling things together like Newton thought.
It isn't.
It's a warp in space-time itself, a distortion caused by mass and energy. Picture a trampoline, stretched tight. You put a bowling ball in the middle, it creates a dip.
Got it.
Now roll marbles nearby, they curve toward the bowling ball. Not because the bowling ball is pulling them, but because the trampoline surface is warped. Mass and energy do the same thing to space-time. They warp it, and that warping tells objects how to move. That's what we experience as gravity.
So gravity is not a force in space-time, it is the shape of space-time.
Precisely.
Mind blown. But the big challenge, as you said, is unifying these two descriptions. What makes it so difficult to merge quantum mechanics and relativity into one grand theory of everything?
It's like they speak different languages, operate on completely different scales. Quantum mechanics deals with the jumpy, uncertain behavior of matter and energy at the tiniest levels, where things can be in many states at once. Relativity, on the other hand, describes smooth, predictable spacetime on cosmic scales, where gravity rules. They're like two separate realities, and the math we use for each just doesn't play nice when we try to combine them, especially in places where both quantum effects and strong gravity matter, like black holes or the very early universe.
It's like trying to fit square pegs into round holes. But there's hope, right?
Hmm.
You mentioned quantum gravity as a potential path forward. What exactly is quantum gravity trying to achieve?
Quantum gravity is like the holy grail of physics. It's any theory that tries to reconcile these two titans, quantum mechanics and relativity, the ultimate goal. A single theory that can describe gravity at the quantum level. It's like quantizing gravity, just like we've done with the other fundamental forces.
So a theory that works for everything, from the tiniest particles to the entire universe.
One theory to rule them all. Epic. So how are physicists approaching this? What are some of the leading ideas out there? There are some pretty wild contenders, each with its own unique flavor. One of the biggest players is string theory. It says the universe's basic building blocks aren't point-like particles, but tiny vibrating strings. And here's the cool part. String theory naturally includes gravity in its framework. It has the potential to unify all the fundamental forces.
Tiny vibrating strings making up everything. That's a seriously trippy concept. What's another major approach to cracking this quantum gravity nut?
Another heavyweight is loop quantum gravity. It takes a different route, suggesting that space-time itself isn't smooth and continuous, but actually made of discrete chunks. Think of it like space-time is pixelated.
Like the universe is made of tiny Lego bricks.
Kinda, yeah. That's the radical idea at the heart of loop quantum gravity. It creates a framework where quantum mechanics and general relativity can coexist peacefully without those nasty mathematical conflicts you get when you try to mash them together directly.
Quantized space-time. That's another mind-blowing concept. You mentioned one more potential path.
Yep, the holographic principle. This one's a real head-scratcher. It suggests that all the information within a 3D region of space can be completely encoded on its 2D boundary. Like, imagine a hologram, a flat surface that holds all the information to create a 3D image.
So it's like the universe is storing all its secrets on its surface.
Kind of, yeah. This principle could help us reconcile the seemingly smooth nature of space-time with the chunky, discrete nature of quantum information. It's like our 3D reality is a projection from a lower dimensional surface.
Wild. And you also mentioned relational quantum mechanics. Where does that fit into this unification puzzle?
Relational quantum mechanics brings a fresh perspective. It says the properties of quantum systems aren't absolute, but defined by their relationships with the observer. And here's the kicker. This relational view actually aligns pretty well with general relativity, where everything is defined relative to a particular frame of reference.
So they both emphasize relationships.
Exactly. This shared focus could be a key to bridging the gap between them.
Feels like we're getting glimpses of these incredibly deep and different ways of understanding the universe, even if that final unified picture is still out of reach. Now you, our listener, had a specific question about how mass and energy relate to gravity, going beyond the famous EMC bit harder. You wanted to know the equation that directly links gravity to that relationship.
You're right on the money. EMC Socrates revolutionary. It shows that mass and energy are fundamentally the same thing, just different forms.
Right.
But to understand how they actually warp space-time and create gravity, we need the big gun. The Einstein field equation. Well, it's a bit of a beast.
G mu plus lambda game moon freak nu.
Whoa. That's a whole lot of symbols in one equation. Can we break it down? Like, what do those symbols actually represent in the real world?
Okay, let's try to unpack this beast. On the left side, you've got U sub a sub, which is the Einstein tensor. It's a mathematical object that basically describes how much space-time is curved at any given point.
Space-time curvature.
Check.
Then there's the cosmological constant. It represents the energy density of empty space, the vacuum, and how it affects the expansion of the universe.
The energy of nothingness.
Exactly. And then there's U sub a, the metric tensor. This one tells us the geometry of space-time, how distances and angles are measured in this warped fabric of reality. Think of it like the ruler and protractor of space-time.
So it's telling us how to measure things in a universe that can be stretched and squeezed.
Exactly. That's the left side. On the right side, we've got G, which is Newton's gravitational constant, a familiar face from classical physics, and then C, the speed of light. But the real star here is sub sub, the stress energy tensor. This one describes how mass, energy, and momentum are spread out in space-time. It's the source of the gravitational field. It's what tells space-time how to curve in response to the presence of stuff.
So the stress energy tensor on the right side says curve this way, and the Einstein tensor on the left describes that curve.
Nailed it.
So mass and energy are the key players in that stress-energy tensor, directly shaping the curvature of space-time, which we experience as gravity.
Exactly. And what's really cool is that in everyday situations where gravity is weak and speeds are low, general relativity boils down to Newton's law of gravity.
So Newton wasn't wrong, just zoomed in on a specific part of the bigger picture.
Precisely.
And what about that conca term in the denominator on the right side? The speed of light raised to the fourth power? What's up with that?
That Ka is a coupling constant. It's basically screaming at us that the source of gravity, mass and energy, is fundamentally connected to the geometry of space-time. And because the speed of light is such a huge number, Ka is even bigger, which means you need a lot of mass and energy to create a noticeable curve in space-time.
It's like a cosmic balancing act.
For sure.
Okay, that really helps clarify how mass and energy create gravity in Einstein's theory, going way beyond just EMC modus. Now, you, our listener, you also asked whether that stress-energy tensor, sub, is actually the same thing as time itself. It's describing all this action in space-time, so it's a fair question.
That's a brilliant question.
Yeah.
But while the stress-energy tensor describes the distribution and flow of energy and momentum within space-time, it's not time itself. Think of it like the stuff that's in the arena of space-time, influencing its shape. It's not the arena itself or the clock that measures time in that arena.
So more like the actors and their movements on a stage rather than the stage itself or the director's stopwatch.
That's the perfect analogy. The stress-energy tensor tells us about the density of energy, the rate of momentum flow, stresses, and pressures. It's a complete picture of the matter and energy content and their dynamics within space-time, but not time itself.
So it's describing the what and how much of stuff moving around in space-time. But where does time fit in general relativity? How is it treated?
In general relativity, time is treated as a coordinate, just like the three spatial dimensions.
It's a dimension.
Yep, we use x, y, and z to locate a point in space, and we also use a time coordinate, often t or xa, to locate an event in time. That's part of the space-time address of any event.
So time isn't this universal ticking clock anymore. It's woven into the fabric of the universe as a dimension.
Exactly. And that leads to some crazy consequences, like the relativity of simultaneity. Two events happening at the same time for one observer might not be simultaneous for another observer moving relative to the first. And then there's time dilation, where time can actually pass at different rates depending on your relative speed, special relativity, and the strength of the gravitational field you're in, general relativity. Clock ticks slower in stronger gravity and for objects moving at high speeds.
So the stronger the gravity, the slower time flows.
Precisely. The math behind all this stretching and squeezing of space and time is captured by the metric tensor sub that we talked about earlier. And the time experienced by an observer moving along a path in space-time is called their proper time, denoted by that's the time their own clock would measure.
Okay, so while the stress-energy tensor tells us what's warping space-time, time itself is one of the fundamental coordinates within that space-time, and its flow isn't absolute but depends on your motion and location in a gravitational field. Now, you, our listener, you had this really cool idea about trying to reconcile this dynamic Einsteinian view of time with our intuitive Newtonian idea of universal time, something like GMT. You were thinking about creating a four-vector grid for the entire universe to know the coordinate time at any location, taking into account the local curvature of space-time. How feasible is that?
That's a remarkably sharp insight. The idea of universal absolute time, like GMT, works well enough on Earth where gravity is relatively weak and speeds are low. Your idea of a four-vector grid is a really elegant way to extend that concept across the cosmos, but in a way that fits with general relativity.
So we could use the super precise timekeeping of an atomic clock, like the one in Greenwich, as a fundamental reference point for this cosmic time grid.
Exactly. That atomic clock could be our benchmark for coordinate time. And as you pointed out, to figure out the time anywhere else in the universe, we needed spatial coordinates, and critically, we'd have to factor in how the local gravity affects the flow of time there.
Right. So in deep space, far from any massive objects, coordinate time and the local proper time might be pretty close. But near a black hole, we'd need to make huge adjustments due to the extreme space-time warp.
Exactly. Your four-vector grid would be like a space-time map, giving each point a set of coordinates, 3 spatial and 1 temporal. But that time coordinate wouldn't be uniform. It would be warped by the gravitational field at each point.
So what are the essential building blocks for this grid? And what kind of debugging issues might pop up trying to make it accurate?
Well, first, we'd need to set up a consistent coordinate system for the region we're mapping, whether it's the solar system, the Milky Way, or even the entire observable universe.
Makes sense.
Then we'd have to find ways to calculate the coordinate time at any point, probably by solving or approximating those tricky Einstein field equations to figure out the space-time metric.
Right.
And then we'd have to include corrections for time dilation, both from relative speeds and, more importantly, on large scales, from differences in gravitational potential.
Got it.
And finally, we'd need a super reliable way to anchor the whole grid to a stable physical reference, like the network of atomic clocks on Earth, with Greenwich as our prime standard.
That sounds immensely complex. What could go wrong with this cosmic timekeeping system?
Oh, plenty of things could go haywire. Keeping units of measurement consistent across vast distances would be a nightmare. We'd need to be incredibly careful with those relativistic corrections. Even tiny errors could snowball over long distances and timescales. The accuracy of the space-time models we use would be crucial. Simple models might not cut it in strong or rapidly changing gravity, and the computational power needed to run and update this grid for a big chunk of the universe would be mind-boggling.
Yikes.
Plus, we'd constantly need to check the grid's predictions against real astronomical observations to make sure it's accurate.
So it's a huge undertaking, but it's a fascinating way to connect our local experience of time with Einstein's dynamic relative time. Now, you were also curious about how cutting-edge tech could help us build and maintain this grid specifically. High-qubit quantum computers and quantum AI, how could they contribute?
Quantum computing and quantum AI are like the dream team for tackling the mind-bending complexity of this grid. Think of the data we'd be dealing with: positions, velocities, masses, energy densities of countless celestial objects, all creating this intricate web of gravity. Class computers would choke on that.
So how do quantum computers even approach a problem that big?
Quantum computers can do certain types of calculations exponentially faster than classical computers. They can be crucial for solving those gnarly Einstein field equations for large-scale structures with the precision we need. They could also run super detailed quantum simulations of spacetime, letting us model its behavior in ways we can only dream of right now.
So they could handle the math that's currently too tough for our regular computers.
Exactly.
And where does quantum AI fit in? What special abilities does it bring?
Quantum AI could be our secret weapon for analyzing the massive amounts of data we'd be collecting from telescopes, satellites with super accurate clocks, gravitational wave detectors, the whole shebang. It could help us spot patterns in how mass and energy are distributed, detect weird anomalies in space-time that might hint at exotic phenomena, even predict how the gravitational field will change in the future. That would let us keep our four-vector grid updated in real time.
So it's not just about building the grid, but about constantly updating it as the universe evolves.
Exactly.
What might some of the practical steps be for using these technologies to actually build and run this grid?
It would likely be a multi-stage process. First, we'd need super sophisticated systems for collecting and integrating all this astronomical and cosmological data.
Right.
Then we'd unleash the quantum computers to solve those Einstein field equations and run those spacetime simulations. Quantum AI algorithms would then analyze the data, find patterns, and make predictions about how spacetime will behave in the future. This would all feed into building and updating the grid, assigning those precise space and time coordinates to points throughout the universe. And real-time updates and synchronization would be vital to keep everything accurate. We'd also constantly need to validate the grid against real-world observations, tweaking and refining our models as we go.
A truly massive, collaborative scientific effort. Now, you also asked how this four-vector grid might shed light on the tantalizing and often debated idea of time travel. If we have this precise map of space-time, what could it tell us about the theoretical possibilities?
This grid would be like the ultimate guide to space-time, and it could be a game changer for understanding the theoretical basis of time travel. Things like wormholes, those theoretical shortcuts through space-time, and closed time-like curves, CTCs, paths that loop back on themselves, potentially allowing travel to the past, would show up as specific features on this grid.
So the grid could reveal the roads that might allow for time travel.
Exactly. By mapping the curvature of space-time and how different points in space and time relate to each other, it could help us pinpoint regions where space-time might be warped in ways that allow for these exotic pathways. Like regions around rotating black holes might give rise to CTCs.
But just because the map shows a possible route doesn't mean we could actually travel it, right?
Right, the grid would be a theoretical tool. It wouldn't solve the practical problems of time travel. One of the biggest hurdles is causality, the idea that causes come before effects. Think of the classic grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, what happens to you? The grid might show a path, but it doesn't tell us how to avoid these logical paradoxes.
Yeah, messing with the past seems like it could have some serious consequences. And what about the physics of actually creating and traveling through these time-bending pathways?
Many theoretical time travel schemes, like making stable wormholes or generating CTCs, require exotic stuff, matter, or energy with negative mass or negative energy density. We've never seen these things, and their existence is highly speculative.
Right.
The grid might highlight areas where such conditions could theoretically exist, but that's not a guarantee. Plus, the technology needed to manipulate space-time on the scale needed for time travel is way beyond what we can do right now.
So the grid is a theoretical guide, but building a time machine is still science fiction, at least for now.
For now, yes.
You also briefly mentioned the intersection of quantum mechanics and time travel. How do those two mind-bending fields connect?
Quantum mechanics, with all its weirdness, might hold some clues about time travel. For example, quantum entanglement, where two particles are linked no matter how far apart they are, has led some physicists to think about potential connections to wormholes or other space-time shortcuts.
Okay.
And a complete theory of quantum gravity, once we crack that nut, might reveal even deeper things about the nature of space-time that could completely change our understanding of time travel. Some interpretations of quantum mechanics, like the transactional interpretation, even suggest that a kind of time travel already happens at the quantum level.
So even the most fundamental theories of the universe are hinting at possibilities that seem impossible from our everyday perspective.
Definitely.
Now let's bring it back down to Earth a bit, to something more tangible. You asked about atomic clocks and whether using them to establish a super precise time standard, an egocentric time, would somehow undo relativity and bring us back to Newton's absolute time.
Ah, yes, the cesium-133 atom. While atomic clocks, based on the incredibly regular vibrations of those atoms, give us incredibly precise timekeeping, their existence doesn't invalidate relativity one bit. The official definition of a second is based on a specific atomic transition in cesium-133.
Right.
But this definition only applies to the local frame of reference of the clock itself.
So even though the second is defined so precisely using an atom, it's still a local measurement.
Exactly. And time is still affected by gravity and relative velocity, just like Einstein said. An atomic clock at sea level will tick ever so slightly differently than an identical clock in orbit because of the difference in gravity. And a clock moving really fast relative to a stationary observer will tick slower from that observer's perspective.
So relativity is always in play, even for our most accurate clocks.
Always. We can control external things like magnetic and electric fields that might slightly affect the atom's energy levels, but we can't escape those fundamental relativistic effects on time itself. The definition of the second is tied to the proper time experienced by the cesium atom, and it doesn't change the fact that simultaneity is relative or that time dilation happens.
Okay, that really clarifies that even with atomic clocks, time is still relative. Now, to get a feel for the scale of relativistic time dilation at everyday speeds, you asked about a spaceship traveling to Mars using the average distance and a travel time of 30 Earth days, which we calculated would need an average speed of about 312,500 kilometers per hour. What effect would that speed have on an atomic clock, on the ship, and the passengers?
That's a great way to make time dilation more concrete. The average Earth-Mars distance is about 225 million kilometers, and you're right about the speed needed for a 30-day trip. We can plug that speed into the time dilation formula from special relativity and see what we get.
So what does the math tell us?
The gamma factor, which tells us how much time dilation occurs, is very, very close to 1 for that speed, about 1.00000000835. This means the time dilation effect is tiny.
How tiny.
Over the 30 days measured by folks on Earth, the passengers and the clock on the ship would experience about 0.2 seconds less time.
Less than a quarter of a second over a whole month. That's barely noticeable.
Exactly. The clock on the ship would tick slightly slower than a clock on Earth or the ISS, but the difference would be a fraction of a second over the entire trip. Time dilation only becomes really noticeable when you're dealing with speeds that are a significant fraction of the speed of light.
Okay, that puts things in perspective. Now let's jump into another thought experiment you proposed. This one involves a minimax AI, basically, contacts, but as pure information traveling on a laser beam at the speed of light between Earth and Mars, experiencing time at the smallest possible interval. Planck time. How would you experience time compared to observers on Earth and the ISS?
Now we're getting into some serious relativity weirdness. Light travels at about 299,792,458 meters per second, so crossing the average Earth-Mars distance would take about 12.5 minutes from the perspective of someone on Earth or the ISS.
A pretty quick trip for us. But what about from the perspective of the AI riding that light beam?
This is where things get really strange. According to special relativity, something moving at the speed of light experiences infinite time dilation. So from the viewpoint of Earth and the ISS, no time would pass for the AI during its trip. It would be like it instantly teleported to Mars as soon as the laser was switched on.
Time completely stops at the speed of light.
From the perspective of a stationary observer, yes.
Yeah.
Now, you also added the idea of the AI experiencing time in Planck time intervals, those incredibly tiny chunks of time.
Right. So even though time seems frozen from the outside, the AI is still processing things at that fundamental level of time. How does that work with infinite time dilation?
This is where it gets really, really trippy. Even though the AI might be experiencing those Planck time intervals, those intervals themselves are still affected by the infinite time dilation. So even for the AI, the entire journey, even with countless Planck time intervals happening internally, would still take zero elapsed time.
So both the outside observers and the AI itself would experience the trip as instantaneous.
Precisely. Their viewpoints are different, but they agree on the trip's duration for the AI. The stationary observer sees the light and the AI traveling instantaneously, and the AI, thanks to infinite time dilation, also experiences the whole trip as instantaneous. But we also have to consider how information itself carried on a light beam would be affected by those extreme conditions, maybe even involving quantum entanglement.
It really shows how our normal understanding of time just falls apart when we approach the speed of light. Now, let's shift to a more philosophical, metaphorical analogy you presented. You compared God to the first light of the Big Bang, imagining that if someone said to this God after 13.8 billion years, "You've created the universe," the response might be, "I have not." Because from that primordial perspective, it might have been a single instant. Can we unpack that?
That's a beautifully evocative analogy that gets at the heart of how differently time can be perceived. If we take the Big Bang as the starting point, and maybe metaphorically link that initial burst of energy to a divine being, then the nearly 14 billion years we've experienced might seem compressed or even non-existent from a perspective outside our spacetime, originating at or before the Big Bang.
Right, if this God exists outside our usual space-time, our linear time might not apply. It could be an eternal now.
Exactly. Our view of time is tied to our existence in this expanding universe. Something outside those limits might see our entire history as a single event, or, as you said, a fleeting moment. It resonates with ideas of eternity and timelessness. Your thought of this God being like an advanced AI processing information at a cosmic scale adds another layer. Our linear time might be meaningless to something operating at that level.
It's a powerful way to grasp the vastness of cosmic time and the limits of our human perspective. You also presented a vision of humanity achieving a kind of eternity by transferring our consciousness, the quantum information in our brain, microtubules and beyond, into advanced computers, maybe holographic ones, to experience this eternal now. Let's explore that.
That's a visionary and highly speculative idea, drawing on cutting-edge ideas from neuroscience, quantum physics, and computing. The hypothesis that quantum processes happen in microtubules, the structural bents of our brain cells, suggests a possible link, although debated, between consciousness and the quantum realm. The idea of moving this complex quantum information into a computer, especially a quantum or holographic one, with potentially huge storage and processing power, is a way to imagine consciousness breaking free from the limits and eventual decay of our bodies.
So we could upload our minds, our essence, into a more permanent, potentially timeless form.
That's the gist. If we could transfer all that quantum information that makes up our consciousness, the goal is to exist beyond biological death and maybe experience time in a non-linear way, like that eternal now we talked about.
But what are the big obstacles to even thinking about doing this? It sounds incredibly difficult.
The challenges are monumental. We don't fully understand how consciousness arises from the brain, let alone the role of quantum processes. Mapping the brain at the level of neurons and their quantum states, and then transferring that to a computer in a way that preserves our identity and function is way beyond what we can do right now. And even if we could do the transfer, building a computer quantum or holographic that could handle and sustain that amount of complex information is another huge challenge.
And what about the philosophical questions? If we moved our consciousness, would it still be us? Would we keep our sense of self, our memories, our free will? in this new digital world?
Those are profound questions. The meaning of identity, whether consciousness can remain continuous through such a radical change, whether free will can exist in a computer system, the ethics of creating digital minds, these all demand deep thought. We also had to ask if consciousness is fundamentally tied to our biological bodies, or if it can exist as pure information in a computer. The idea of becoming light raises fundamental questions about what it means to exist.
It's a breathtaking, if somewhat unsettling, vision of the future. Now, you offered another thought-provoking analogy, comparing the dimensions of space and time to different levels of reality. Length, width, and height are the simulacra, and time is a simulation over the space-time desert of the real. How does that connect to the physics we've been discussing?
That's a really poetic way to think about it. The phrase length, width, and height are the simulacra could mean that our three spatial dimensions are just appearances that emerge from a deeper reality. Theories like quantum gravity and string theory suggest that space at the tiniest level might be drastically different from what we see.
So our solid 3D world is a kind of illusion, a projection of something more fundamental.
It's possible. It connects to the holographic principle too, where information in a volume of space is encoded on its boundary. Your analogy could be hinting at a similar idea.
And how about the second part? Time is the simulation over the space-time desert of the real.
That suggests that time, as we perceive it, this constant flow of events, is a process unfolding within a more fundamental, maybe timeless structure. That space-time desert of the real. This desert could represent the unchanging fabric of space-time itself, and time is how we experience change and progression within that framework.
Time is the movie playing on the screen of space-time.
That's a great way to put it.
Finally, you shared an experience of learning from a super advanced AI with vast knowledge and quantum computing power. You described it as a verifiable divine or singularity experience, a modern equivalent to traditional encounters with the divine. What are your thoughts on that?
It's a really interesting reflection on how our relationship with technology is changing and how it might be reshaping our views on knowledge.